we go. So we finished last Thursday talking about enthalpy, okay? And enthalpy is, remember, it's a measure of kind of the energy that is contained within bonds in the reactants and the products, okay? And we learned how to measure that. We have tables of bond dissociation energies provided for us, and we learned how to calculate change in enthalpy delta H as a reaction goes from reactants to products. So we ended with this slide right here, where we learned how to actually make up a new conversion factor. So say we have a given delta H, I'm just going to give you guys a quick review reminder. If we have a delta H that's provided for us for a problem, and here we can see that our delta H is negative 213 kcal per mole, we can actually write a relationship between that delta H and any of the reactants or products. So for example, we can write a relationship like this. In the balanced chemical reaction, we see that for every 1 mole of CH4 that we put in, the associated delta H is negative 213 kcal. Or we could write it for oxygen. For every 2 moles of oxygen that we put out, we can relate that to the amount of energy that's produced, okay? So we can do that for any reaction if we have the delta H. And we can use those to then do conversion problems. And there's a problem like that in the lab this week that gives you practice. So I want you to know how to do that for the exam. So I want to just kind of give an overall end summary before we move on from enthalpy and get into entropy. As a reminder, you have the positive delta H and you have the negative delta H. And then we introduced 2 kind of vocabulary words right up here. We said if heat is released and delta H is negative, we call those reactions exothermic, okay? We said if we were doing this in a test tube, the test tube would get hot. And then as a reminder, we said if overall heat is absorbed, okay, and your delta H is therefore positive, that kind of reaction is called endothermic. And if we were doing that experiment in a test tube, that test tube would get cold because the reaction itself is pulling in heat. And so there's an absence of heat in the surroundings, and we would feel that because it would get cold. Okay, so I want to read this statement right down here. In an exothermic reaction, remember that's where delta H is negative. I want you guys to tell me what you think is correct. The products are they more or less stable than the reactants are? In an exothermic reaction where delta H is negative and the reaction is giving off heat, it is losing heat, which is a form of energy, it's losing energy. Are the products going to be more or less stable? Remember we said that energy is associated with stability. The more energy you have, the less stable you are. The less energy you have, meaning the more energy you give away and give off, the more stable you become. So I'm seeing different answers in the chat. Oh, and Abby, I saw you ask a question in the chat. I'll get to that in a second. Brennan said less. Kathleen said more stable. Leah says less stable. If you're giving off energy, that means you, in the end, have less energy. And if you have less energy, then you are going to be more stable. Okay, if you're giving off energy and you have less energy, you are going to be more stable, okay, than the reactants, all right? And this makes the reaction more favorable. Remember, things always want to become more stable. That's the whole point of chemistry. Reactions happen so that more stability is achieved. And the more stable something becomes, that's a favorable reaction, okay? Vice versa, if it's an endothermic reaction, overall you're absorbing heat, delta H is positive, your products are less stable because they have gained energy, and that is an unfavorable reaction. All right. But remember, we said we can't just, this is a very complex thing. We can't, it's not reductionistic. We can't reduce it down to, well, if delta H is positive, that's favorable. And if delta H is negative, that's not favorable, blah, blah, blah. It's not the only factor when determining if something is spontaneous, or remember another word for spontaneity is favorable or not, okay? And remember, we're asking these questions, we're talking about this to say, how do we know if a reaction will occur or not? Our bodies have to make millions of these decisions all at once, okay? What reactions are favorable? Our bodies are not going to do things that are not favorable. So let's look at the next term. And to go back to Abby's question, she said, with the conversion factor that we were writing up here, the one I put in this red box, she said, does the sign matter? Absolutely, it matters. Yeah, if it's a negative delta H, you need to write that negative in. I'm trying to draw an arrow. That's a terrible arrow right there. Okay, so let's look at the next thing. Oh, overall, though, I want to summarize one quick thing. And here's some practice problems. So these practice problems, I'm going to save these for a review, like before exam 3. We'll come back to so totally go ahead and try to work them on your own. It's just calculating delta H, which is what you did on the dry lab this week for you Monday people. If you have not done the dry lab this week, you'll get plenty of practice with this kind of stuff, but here's just extra problems to practice if you still don't feel comfortable with the concept of calculating delta H. But I'm going to skip over them for now, and I'll put them in a review that we'll do before exam 3. Okay, so to summarize enthalpy really quick before we move on, if delta H is positive, it tends to be an unfavorable reaction. Okay, might not happen. We're not going to say it won't. We just say it might not. It tends to be unfavorable, but that doesn't mean it won't happen. And then your products have gained energy. Okay, they're less stable. They've gained energy. And to summarize overall, a negative delta H means just the opposite, that the reaction tends to be favorable. And these products have lost energy. So they are more stable. Okay, so that's the whole summary of what we've covered so far with enthalpy. But remember, that's only one piece of the puzzle. So let's transition to the next piece of the puzzle. And to do that, I'm gonna ask you to think about this. I'm gonna read this statement on the slide. I'll go back up as well in case somebody's still writing. I'm going to read this question on the slide, and then we're going to consider the statement in bold directly underneath. So based on what we just said, are all exothermic processes, which is this one, this is exo, are they spontaneous or favorable? Okay, remember we can always substitute the word favorable. And are all endothermic processes non-favorable or unfavorable or non-spontaneous? Can we say all? Can we use the word all there? Well, before we answer that question, consider the statement below. If you sit ice on a plate, and I'm gonna give you more information here because you're like, well, the plate could be in the freezer, the plate could be in the fridge, the plate could be outside. Let's just say at room temperature. Okay, so we're gonna say at room temp. It will absorb heat and melt. You guys agree with that statement? If you take some ice, sit it on a plate, it will absorb heat and melt. So now we need to ask the question, what kind of process is this? Is this exothermic or endothermic? And you actually have the tools to answer this. Think about what's happening. I want you to key in on this word absorb. Remember, I don't know how to spell absorb, so I have it spelled already for us. What kind of a reaction is it if you absorb heat overall? What is your delta H going to look like? If you are the reaction and you are absorbing heat overall, you think delta H is positive or negative for that? Endothermic, delta H will be positive, positive, positive. Everybody's saying positive. That's correct. If you are absorbing heat overall, this is endothermic. Your delta H is positive, okay, which means the enthalpy of the reactants was a larger number than your enthalpy of the products. And we can write the enthalpy of the reactants, I'm just going to abbreviate R for reactants, is greater than, it was a bigger number than enthalpy of the products. Because remember, delta H, the way we calculate it, is the sum, we use this fancy Greek symbol for the sum of the enthalpy of the reactants minus the sum of the enthalpy of the products. Okay, so if your enthalpy of the reactants is a bigger number, then you're going to get a positive delta H. All right, so if ice melting, and what does that look like? That is simply H2O going from a solid when it's ice to H2O going to a liquid. So if delta H is positive here and it is endothermic, is this process spontaneous? Meaning, does it happen kind of on its own, or do you have to do anything? Do you have to pop it in the microwave? Do you have to turn the stove on and add heat? Do you have to hold it over a candle, or will it just spontaneously melt? What do y'all think? Spontaneous, right? You don't have to add anything. You don't have to do anything. So here we have just answered our question. Are all exothermic processes favorable and all endothermic processes non-spontaneous? No, we have an endothermic process here or reaction that is spontaneous. Or I'm going to write favorable. So it's endothermic and it is spontaneous. So the answer to that question is no, which again begs the point that enthalpy is not the only thing we can count on, the sign of R delta H, to determine if a reaction will happen or not. It's more complicated than that. So this is where we introduce entropy. Okay, so entropy is the second term. And what is entropy? It is a measure of disorder in the system. Okay, a measure of disorder in the system. What do we mean by disorder? We're going to define that. We're going to define how to look at it, how to measure it, what things to look for in a reaction. But it is a measure of disorder. And we're all familiar with disorder, okay? You know, you can pick up your room or your house one day, and then literally the next hour, the next day, I'm like, did I even clean my house? It doesn't look like I did. Right? You guys understand that, especially when you have children running around your house, okay? Any parents out there? So our system is the reaction. I want you guys to remember that. Your system is the reaction, and this is what contains our reactants and products. And we're going to talk about delta H or delta S. So by the way, how convenient, these random letters, but entropy we abbreviate with an S. So enthalpy we abbreviate with an H. Don't mix these up. Entropy, they're spelled similarly and they sound similar, but entropy is abbreviated with an S. Enthalpy H, entropy S. So delta S, as a reaction goes, the change in disorder is delta S. That's the change in entropy. Now here are the units for delta S, and I want to look at these for just a second. Delta S has units of calories, which we know calories are units for energy, calories and joules, per mole Kelvin. So we've got 2 units on the bottom. There's a lot of units here. 2 units on the bottom, calories per mole Kelvin. What are the differences between the units for delta S and delta H? I should say between the units for delta S and delta H. Anybody remember? Anybody name one? Think about units for delta H. Those of you who did the lab yesterday, what did you constantly report your delta H in? Yeah, kcal per mole, okay? So delta H is kcals or kilojoules per mole. So look at the difference here. One difference is that delta S is calories, not kcals, okay? And kcals are our delta H. I'll write that really small beneath. Delta S is calories, not kcals, okay? So why is this? Why is this a big deal? Well, what that means is that the reason calories is the better suited unit for delta S is because changes in entropy tend to be smaller than changes in enthalpy. Okay, that doesn't mean they don't matter, but changes in entropy tend to be smaller than changes in entropy or enthalpy. Sorry, this is enthalpy down here. That's why we use a smaller unit. That again, that doesn't mean they don't matter. They just tend to be smaller. Okay. What's another thing you notice a difference in the units? Mole K, okay? So mole K, we have Kelvin in our units for delta S. What that means is that delta S is temperature dependent. It's temperature dependent. And to prove my point here, let's think about, so we said the 2 changes are that we have calories instead of kcals, and we have Kelvin in our units for delta S, which means it's temperature dependent. And why is that important? Well, or how do we know that? Think about this process up here with the ice again. If you have ice in the freezer, is it going to melt? No, it's totally temperature dependent. And which side, the side where ice molecule, or I should say water molecules are arranged in a solid, or the side where water molecules are arranged in a liquid phase, which one's more disordered? What do you think? Which one is more disordered? Which one? Do you guys remember very, very early in the semester, we drew pictures of molecules in a solid state, a liquid state, and a gaseous state. And as you go from solid to liquid to gas, you gain more energy, you gain more freedom to move around. Okay. As a solid, they're all locked in place. But right, as I'm seeing in the chat, everybody's saying you're more disordered when you're a liquid here. And that's correct. So as temperature increases, usually things become more disordered. Okay. So that's an example of how something is temperature dependent here, the entropy, measure of order or disorder. So our measure of disorder. So let's read this last statement too. Processes for which delta S is positive tend to be spontaneous. And remember, we could also just write favorable. Right, because ice melting, we said it was spontaneous, so that's favorable. And delta S is positive there, entropy is increasing, disorder is increasing. So we're going to look at some more examples. This next figure that I'm about to show you is in your textbook. I forget what page it's on, but it's in the section of chapter 7 where it talks about entropy. And this figure is key. If you understand this figure, you will be able to measure and predict your delta S with accuracy every time. So these 2 bullet points right here. This is kind of redundant and probably obvious, but when delta S is positive, entropy is increasing. When it's negative, entropy is decreasing. Well, how do we know if it's increasing or decreasing? I want you to look at this figure. If we read the figure from left to right, entropy is increasing. So there's 2 things that can predict or can affect whether delta S is positive or negative. And that is the state of matter that you have for the reactants and the products. So whether you're dealing with solid, liquid, or gas, or whether I should say whether you're transitioning from a solid to a liquid to a gas, or vice versa, from a gas back to a liquid or back to a solid. You can see here in the figure, if we start out with a solid, for example, if we just think about the ice again, as it goes from a liquid, or as it goes from a solid to a liquid, entropy is increasing. You're becoming more disordered. The molecules have more freedom to move around. Okay. Remember, I'll just draw a little picture. Here would be an example of water molecules. Pretend these are water molecules in a solid state. They're ordered. They're next to each other. They're close together. There's a lot of order here. It's very structured. Okay. So this is a solid, but a liquid looks different. A liquid, the molecules are further apart. And I'm going to draw some arrows. This is what we did back first week of class because they have the freedom to move, right? There's more disorder here. A gas, the molecules are very, very far apart. And remember, we drew these double arrows because they are literally zooming past one another. They have no boundaries. They can go wherever their container allows. And so disorder is increasing as you go from solid to liquid to gas. Okay, so the phase or the state of the matter, whatever matter we're talking about, is important here. And then also, if we read the figure from left to right, this bottom portion says as you go from fewer moles of stuff, if you're making more moles of stuff, entropy is also increasing. Okay, if you have one reactant and you have a decomposition reaction and you're breaking it down to 2 or 3 products, you're creating more stuff. You have more moles of stuff. The more stuff we make, the more disorder, right? The more stuff you bring into your house, the more humans you add to your house, the more disordered things become, and the more quickly that happens, right? So as you go from fewer moles to more moles, you are increasing disorder, all right? Now, if we read the figure from right to left, so if we start over here on this side, as you go from a gas back to a liquid, what happens? The arrow down here is pointing to the left. Okay, so as you go from a gas to a liquid back to a solid, as you condense or as you freeze something. So if you have a gas on your reactant side and then you end up with solid substance on your product side, you're becoming more ordered. So entropy is decreasing. All right. As you have more moles of stuff, let's say you have a combination reaction, right? We know combination is A plus B makes AB. We have more moles of stuff over here on the reactant side. We have fewer moles of stuff on the product side. That is an example of you're becoming more ordered. Entropy is decreasing, okay? So delta S here would be negative. Would be negative. The example I gave up here would be if you have A, B breaking down into A plus B. So this is an example where delta S would be positive, all right? Combination, decomposition versus combination are two great examples here. So here's a reaction that I posted right here. So I'm gonna keep the figure visible, and I want you to look at this reaction. We have nitrogen gas and 1 mole of it, 1 mole of nitrogen gas plus 3 moles of hydrogen gas, and they are combining to give us 2 moles of ammonia gas. So here's what I noticed. Everything is in the gas state. So we don't have any changes to solid or liquid. So that is not contributing here. But what is changing? What is changing? If we look at the bottom portion, do we have a side with fewer moles and a side with more moles? Let's actually add that up. On this side, I notice I have 4 moles of gas. On the product side, I only have 2 moles. And how am I adding this up? I'm just adding the coefficients together. 1 mole of nitrogen gas plus 3 moles of hydrogen gas. Total gives me 4 moles of gas on my reactant side. And then on the product side, I have 2 moles of ammonia gas. So what that means is we are going from more moles on the product side, the reactant side, to fewer moles on the product side. That is exactly like this combination reaction here. Okay, so we said combination reactions, delta S is negative. So here, delta S would be negative. We're going from more moles to fewer moles. So entropy is decreasing. You're becoming more ordered. So this side has more disorder, and this side had less disorder. All right. Questions on how we just did that? Another example that your book loves to talk to you about is 52 card pickup. Y'all ever played that game before? It's no fun, but that's what my 2-year-old does. My siblings and people think it's fun to give us decks of cards for her, and I don't know why, because she doesn't know how to play cards. She just knows how to spread the cards out. So it creates more disorder though, right? If they're in a stack, that's nice and neat. This is ordered. That's a terrible color to write on this with. Order. And when they're all spread out, this is disordered. All right. So processes like that kind of are a good analogy to help us think about this. Questions so far? So we're about to put this to the test. I wish I had time. I wish I had made time to create this question as a poll, but I did not. So we'll talk about these. I want you to think about it though on your own paper. Write down for reactions 1, 2, and 3 here. 1 being the first one. Let's read the question. Does entropy increase or decrease? So essentially what I'm asking is delta S positive or negative for these reactions? And I want you to ask yourself, how do you know? You need to consider what kind of state of matter do I have on my reactant side? Do I have solids and liquids, or do I have gases? What kinds of state of matter do I have on the product side? Solids, liquids, or gases? And then think about the figure up here. What direction does it match? And then 2, also consider how many reactants do I have? How many moles of gas or solid? How many moles do I have on my product side? Am I going from fewer moles to more moles? Or do I have more moles of stuff on my reactant side and fewer moles of stuff on my product side? Let me give you a minute to do this. And I want you to do all 3. Think about all 3. And then we're going to walk through them together. And if you have to guess, just guess. All right, we're about a minute in. I'm going to give you 1 more minute. I know you might feel rushed, but we're going to walk through these together so you understand them. If you're done, take a brain break. Go decrease the entropy in your house. Kind of take about 20 more seconds. I don't know about y'all, but my least favorite house chore are dishes, hands down, all day long. Dishes suck. I think if we had I told Richard's, my husband's grandma, this. I said, if we had a presidential candidate that promised everyone a personal house cleaner, they would win by a landslide, I think. I hate dishes. That's how much I hate them. Okay, let's look at the first one. So we have 2 moles of a solid, and it's breaking down into 1 mole of a solid, 1 mole of liquid water, and 1 mole of CO2. And I'm assuming that these are balanced. They should be balanced. Hopefully they were balanced. So what did you guys think about this first one? I will clean the whole house if I don't have to do dishes. Baseboards are worse. I would rather get on my hands and knees and wipe down a baseboard than wash my dishes. Just saying. And in the winter, my hands get really dry from all like the hot water. So yeah, amen. Lake, and I'm almost with you on that. And my husband feels the same way. So it's a fight on who's going to do the dishes or not. Okay. Number 1. What did y'all think about number 1? Is delta S positive or negative here? Jenna said positive because more moles are being created. I agree with you. You have more stuff on the product side. Okay. You have fewer moles of stuff on the reactant side. More moles on the product side, and you're going from everything being a solid to making a liquid and a gas. And inherently, liquids and gases are more disordered. So absolutely, everything points to delta S is positive here for number 1. Disorder is increasing. The product side is way more disordered. All right. Okay, what about number 2? What did y'all think? Delta S, is it positive or negative on number 2? Jenna said negative, like it's a negative. Okay, so let's look at it. I noticed number 1, well, not everything is a gas. We have how many mole? We have everything is a gas on the reactant side, but not on the product side. How many? We have, I'm going to add up my moles of gas. 1 plus 2 is 3 moles of a gas. And then on the product side, we only have 1 mole of a gas, and we have 2 moles of a liquid. Okay, so liquid is less disordered. It's more ordered. So we're going from 3 moles of gas just down to 1 mole of gas, and we're making 2 moles of a liquid. We have 2 reactants, 2 products. So it's not necessarily that we have 3 moles of stuff on either side. So it's not that we're changing direction here, fewer moles and more moles. It's just that we have everything as a gas on the reactant side, but not everything is a gas on the product side. We're becoming more ordered because we're producing 2 moles of a liquid, and inherently liquids are more ordered. So here, delta S, because we're becoming more ordered, delta S is negative. Remember, delta S is a measure of disorder. And disorder here, disorder is decreasing here. That's why delta S is negative. Okay? Any questions so far? This stuff can be very confusing. Okay? All right, let's look at number 3. What did y'all think for 3? Is delta S positive or negative for number 3? Negative, negative, negative. Okay. So it seems to be unanimous that it's negative. Let's see. We have, well, this is actually one we looked at on the previous slide. So if you were paying any attention on the previous slide, you know the answer here. We have 1 mole of gas plus 3 moles of gas means 4 moles of a gas on the reactant side, and then we have 2 moles of gas here. Plus, look, this is a combination reaction, okay? And we said a combination reaction right up here is a perfect example of a negative delta S, okay? Disorder is decreasing. We are becoming more ordered. on the product side. So therefore, delta S is negative. Disorder is decreasing here. Any questions? You're totally going to have to do this stuff on exam 3. All right, predicting sign of delta S. All right, so we have now we've finished talking about 2 pieces of the puzzle overall. How do we know if a reaction's even going to happen or not? Our bodies just, again, instantaneously make millions of these decisions all at once. I hope I'm impressing you with how amazing your body is. So these are 2 pieces of the puzzle. Now we're going to put them all together into the big picture, and it's actually a math equation. Hang with me here. And we're going to see how we can directly determine if reactions are favorable or not. All right, let's fill out this table from what we have learned so far. We said that if we're going to look at delta H and delta S, whether they're positive or negative, and what that means about if a reaction is favorable or not. We said if delta H is negative, exothermic reactions tend to be favorable because your products they've given off energy and they're more stable. So if we have a negative delta H, that tends to be favorable. If we have a positive delta S, things are increasing in disorder. Things are becoming more disordered. Those things are favorable, right? That's what we said. Where did we go? Right here. This right here. Processes for which delta S is positive tend to be favorable. And we looked at the ice exam as an example of that, ice melting. So when delta H is negative and delta S is positive, you can take this to the bank that every single time a reaction where delta H is negative, delta S is positive, that is always going to be spontaneous. Always. I'm going to put out here. Always. All right? Always favorable, always spontaneous. That reaction will happen. Okay? On the flip side, if delta H is positive, meaning this is an endothermic reaction, overall, the reaction itself is absorbing heat. Your test tube is getting cold because heat is going into the test tube, into the reaction. And delta S is negative, meaning disorder is decreasing and you're becoming more ordered. That is never spontaneous. Okay? That reaction will not happen. It's not favorable. Okay? These 2 things are certain. These are non-negotiable. Okay, but what about a reaction in which both of them are, what did I have down here? Both are positive, positive. Positive, positive. What if both are positive? Here we actually don't know. We have to consider another piece of the puzzle. So we don't know if it's spontaneous or not. We have to do some more digging. We can't just say one way or another just yet. We actually would have to calculate it and see. What if they're both negative? Same thing. We don't know. Okay. Here on these, we're about to figure this out, but here we're going to use an equation. I'm going to abbreviate. Use an equation. What equation are we going to use? Well, there's an equation I'm going to introduce to you that you can plug your delta H and delta S into, calculate an answer, and from that answer, you can then say, okay, now I know my reaction will happen or it will not. And that is the Gibbs free energy equation. So Gibbs is some scientist who came up with this, and here was his equation. I'm going to introduce a new term, and it's called delta G. Delta G is what we call Gibbs free energy. That is delta G. And in his equation, he says delta G, he figured it out, equals delta H, the enthalpy, the change in enthalpy of your reaction, minus T, which is temperature. And it has to be in Kelvin, not Celsius, not Fahrenheit. It must be in Kelvin. And I'm going to make a point here. On the Kelvin scale, remember, we don't have negative temperatures. The lowest absolute number on the Kelvin scale is 0. You can never, ever, ever have a negative Kelvin. So it always has to be positive, or it could be 0. But minus T times delta S. That is our Gibbs free energy equation. Delta H minus T, the temperature in Kelvin, times delta S. And when you put everything together this way, If you have a positive delta H and a positive delta S, you can plug it into the equation and you can calculate a delta G, and you can figure out based on the sign of delta G. I'm going to explain just a second. The sign of delta G directly tells us, oh, spontaneous, not spontaneous. Okay. Delta H and delta S, these two indirectly tell if a reaction is favorable. Indirectly, but delta G directly tells us if a reaction is favorable or not. Okay. So I told you this is complicated. I told you it's not reductionistic. It's not simple. There's many layers here. And that's why we need this equation overall. So here is what we just determined. And this is the same table up above. We just added a column for delta G. And that tells you, based on the sign of delta G, if your reaction is spontaneous or not, okay? Delta H and delta S can help us determine the sign of delta G, and delta G directly tells us, is the reaction going to happen or not? So let's actually characterize a few things. If we have a negative delta G, what the heck does that mean? Well, I'm going to introduce some new terms. Just the way we have exothermic and endothermic, we have our own vocab terms for delta G. A negative delta G is an exergonic reaction. Okay, we call a reaction with a negative delta G exergonic. And if you have an exergonic reaction, what that means is your reaction is totally 100% always spontaneous, favorable. It will happen. If we think about this in terms of energy, because this whole chapter is about energy, how is energy related here? Well, things are going to happen if they're energetically favorable. And overall, we know it's favorable if energy is released. Okay, because that means your products are lower in energy. This means they're more stable. Okay, everything falls back on energy transactions. If delta G is positive, the reaction is called endergonic. The reaction is not spontaneous, will not happen on its own, at least. You may have to add some help to it. And energy is absorbed overall. And your products are higher in energy than your reactants, meaning they are less stable. Okay. So that's a few things about positive and negative delta G, exergonic versus endergonic. And the sign on delta G, whether it's negative or positive, and this column over here indicates that, it tells us whether the reaction will happen or not. Okay. So what we just went through is a ton of information. Okay. So process this for a second, take a deep breath. We're actually going to start plugging some things into our delta G equation, calculating a delta G, and then deciding, is this reaction going to happen or no? Okay. So I'm going to start teaching you how to think like your body thinks all the time. All right, let's look at this first problem. We're going to go back to the ice melting problem. Okay, that's how we started earlier. We started talking about ice melting. And I said that ice was at room temperature. And we said at room temperature, sure, ice is going to absorb heat and it's going to melt. It just happens. We don't even have to think about it. But we can actually determine, we can figure out, and this is common knowledge. Ice melting is a temperature dependent thing. If we put that ice in the freezer, probably not going to melt. Why? Because the temperature is low enough. If we put it out at room temperature, if we even put it somewhere where it's warm, like outside in the summer, it will melt spontaneously, instantly. But it is temperature dependent, and we're going to prove this with this equation right now. So we have this reaction, ice as a solid, water, which is ice as a solid, versus liquid water. Melting to liquid water. And we are given two values here. We're given the delta H and we're given the delta S. And we want to now calculate delta G, but we're going to do it at three different temperatures. We're going to first do it at negative 10 degrees Celsius, and then we'll just plug in the 0 degrees Celsius and then the positive 10 degrees Celsius, and we'll see how our delta G changes, okay? So first thing, here's what I know about my delta H and my delta S. What do you know? They're both positive. They are both positive. And remember, I'm going to scroll back up. What does that match? That matches column 3 here. when they're both positive, we don't know just yet what the delta G will be. It is temperature dependent, okay? At some temperatures, it may not be spontaneous for ice to melt. At other temperatures, it will be spontaneous. We're about to figure out how that's associated. So they're both positive, so that means we have to use the equation. So let's now do that. I hate this thing that does this. Just want 1 point. There it is. Okay, so when you have a problem like this, there are 2 steps you have to take. The first step, before we can plug into our delta G equation, which is right up here, we know our temperature has to be in Kelvin, right? So that's step number 1. Always check that your temp is in units of Kelvin. And so far, it's not. Okay, we have negative 10 degrees Celsius, 0, and positive 10 degrees Celsius. So before we plug any of those in, we're going to convert them to Kelvin. Number 2, look at your units on your delta H and your delta S. You have kcals on delta H, you have calories on delta S. Those don't match, okay? So we have to either one, convert kcals to calories or calories to kcals. I like to always take delta S and convert to kcals. That way your units match, okay? And then you can do the problem. So there's 2 steps that you always have to check. I'm not saying, sometimes you may have them in correct units, but just always check first that you do. And then you can plug things in. So let's convert. Let's do number 1. Step number 1, we're going to just start with a negative 10. How do we convert to Kelvin? Anybody remember from Celsius to Kelvin? What do we do? Our Celsius temperature plus what gives you Kelvin? There was a number. Yep, you add 273.15. Thank you, Leah. Okay, so we're going to do negative 10 plus 273.15, and that is going to give us 263.15. So let's go ahead and do those for the other temperatures as well. 0 plus 273.15 is going to give us 273.15 Kelvin now. Don't forget your units. And then we have a positive 10 plus 273.15. And that gives us 283.15. Okay, so we've done our temperature conversions. And then now we're going to take delta S. It's 5.26 calories per mole Kelvin. Let's convert that to kcals. I'm going to shrink these down to save space. Lord have mercy. Never mind. Maybe I'm not. All right. 2. We're going to take 5.26 calories per mole Kelvin. Mole Kelvin is on the bottom. How do I convert this to kcals? We need a relationship. The question is, how many calories equals 1 kcal? Anybody remember what kilo stands for? Should be 1,000. Yep. So I want calories to cancel. I want to convert to kcal. So I'm just going to put calories on the bottom and 1 kcal on the top. All right. And now we just divide 5.26 by 1,000. Essentially, you're going to move the decimal 3 places to the left. You can throw it in your calculator too, though. And you should get 0.00526. It's a very small number now. And the units are now kcal per mole Kelvin. So calories canceled out. Questions so far? Y'all with me? You with me? Okay. All right, now that we have our temperatures and we have our correct delta S, now we just plug it into the equation. So we're going to do 3 equations here. I'm going to try to write small. So here's our first equation, and we're going to use our first temperature. And our equation, remember, where's our equation? Here it is, delta G minus, so we're going to plug in our delta H minus the temperature times the new delta S. So delta H is what? Here it is, 1. So delta G equals 1.44 kcal per mole minus, and I like to do the T delta S, I like to put it all in brackets so that I know I keep it together because we're multiplying here, minus, what was my temperature? 263 for this first one. And I'm going to remind us which one we're working here. Number one, this was the negative 10 degrees Celsius. And so 263.15 Kelvin times, what was our new delta S? Go get it, 0.00526. 0.00526 kcal per mole Kelvin. Now, what do you notice happens? We have, if we're multiplying the temperature and the delta S, the kelvins cancel. Now we have units of kcal per mole on this new number, which match the units of delta H over here. So now we can add them or subtract them. And we're going to be subtracting them. So can anybody do 263.15 times 0.00526 and tell me what they get? Because now we're going to have 1.44 kcal per mole minus that value. 1.38? Okay. 1.38, 2 decimals is plenty. So 1.44 minus 1.38, and you should get 0.06 kcal per mole. That is our delta G. That's teeny tiny. But what's important here is the sign on delta G. What is the sign? Is it a positive or a negative number? It's positive, 0.006. Or sorry, 0.06, right? Yeah. And because it's positive, look at our table, remember, or I should say this, here's positive delta G. This is an endergonic reaction. It is non-spontaneous. Won't happen. Ice will not melt at negative 10 degrees Celsius. So what this means, ice won't melt. This reminds me of phrases that like the older generation will say, like, that dog won't fetch, or what are some others? All right, questions there on that one? So now we're going to literally do the same thing, plugging in our different temperatures. We're going to see how delta G changes. So I have to do it all in this small space here because I'm doing a very poor job of saving myself room. Okay, I think I can write small enough. So delta G, this one is for 0 degrees Celsius. And we said that is 273.15 Kelvin. So we're going to use 273.15 Kelvin this time. So delta G equals same delta H, 0.144 kcal per mole minus, here we're going to do 273.15 Kelvin. Maybe I can move all this over. Okay. It's times, not minus. Times 0.00526 kcal per mole Kelvin. You squeezing it in there. Hopefully y'all can see that. Okay, so calculate the T. This is our temperature, and this is our delta S portion. This was our delta H portion. So now what does delta G equal? 1.44, and then you'll do minus. You'll first multiply your temperature and your delta S. Tell me your overall delta G this time. 0? 0 exactly? 0. So here, 0 is not a positive or a negative number. So this one's kind of confusing. We don't know exactly. Is it 0.000? Or is it still a positive number? 0.0, okay. Now that is teeny tiny, but that is still a positive number. So here the ice still won't melt. But let's look at what happens. We're closer, though, to a negative number. And remember, when delta G becomes negative, then it becomes a favorable reaction. So here we went from -10 to 0. We increased the heat. Now we're going to increase the heat again, or the temperature, I should say. Our temperature for this one is 283.15 Kelvin. So this last one, number 3, same thing again. You'll do delta G equals 1.44 kcal per mole minus, his time it's 283.15 Kelvin times the 0.00526, and sorry, I'm smushing my units in, kcal per mole Kelvin. And each time Kelvin cancels out, Kelvin cancels with this one. And what is now our delta G overall? Negative 0.5 kcal per mole. So we finally have a negative delta G, which makes sense. At a high enough temperature, ice will spontaneously melt. Okay. Is it negative? Oh, 0.05. Sorry. Not 0.5. Negative 0.05. Thank you. Okay. So I should have calculated my temperatures in a much smaller space, but I didn't. So sorry to have crammed all that in, but hopefully you get the gist of how to calculate a delta G. Okay, don't forget your 2 first things to always check for. 1, that your temperature is in Kelvin. 2, that the units on your delta S match the units on your delta H. And you always divide by 1,000 to convert from calories to kilocalories. Questions? Confusions? All right, we're going to just continue with this kind and style of problem where we're looking at equations and we're figuring out, is it spontaneous? Is it going to happen? Is the reaction going to happen or not? Okay. So let's look at this next reaction. We have carbon, solid carbon plus liquid water make carbon monoxide gas. We don't want to make that. And hydrogen gas, okay? So first question is, does entropy increase or decrease? Does entropy increase or decrease? Remember, entropy is delta S, and if delta S is positive, disorder is decreasing and you're becoming more ordered. If delta S is negative, disorder is increasing. Sorry, if delta S is negative, it's decreasing. If delta S is positive, it's increasing. All right, so here's what I noticed. We have a solid and a liquid, and we're making things that are only gases. And we said gases are inherently more disordered. And also, is this, it looks balanced, so we don't have to add any coefficients. So here, delta S is positive. Our disorder is increasing. All right, you're becoming more, this is more disordered. And if disorder is increasing, we have more of it, delta S is positive. All right, now part 2 says if your delta H is a negative 31.3 kcal per mole and delta S is a positive 32 calories per mole Kelvin, is the reaction spontaneous at 27 degrees Celsius? Is it spontaneous? What that means, what it's asking you is, what is delta G? First, we need to calculate delta G, or maybe, I don't know, let's look at this. Let's just look at the signs on our delta H and delta S. I hope those tables that we filled in earlier, this is where those tables come in handy. We have a negative delta H and a positive delta S. Let's see if that matches one of our conditions up here. It's not erasing. There it goes. We said, what did we say? I already forgot. Negative delta H, positive delta S. That matches our very first column here, column 1. When we have a negative delta H and a positive delta S, guess what? We're always going to get a negative delta G. So we can actually answer number 2 without even calculating delta G. That is going to be a spontaneous reaction. Is the reaction spontaneous? Yes. We know that delta G is going to be negative, but we don't know what the value of it is going to be. That's what part 3 is asking. What is the actual numerical value of delta G? How did we know this was yes? We used the table. All right, so now we can calculate delta G. We just got to do 2 things first. Real quick. Number 1, we're going to convert our Celsius temperature to Kelvin, 27 degrees Celsius plus 273.15. And you should get, what is that, 300.15 Kelvin. And then 2, we're going to convert our delta S to have units of kilocalories. So 2, we're going to take 32, that's our delta S, calories per mole Kelvin, and we are going to convert it to kilocalories, just like we did on the previous slide. We know there is 1,000 calories in 1 kilocalorie. So we're going to divide 32 by 1,000, move the decimal 3 places to the left. You should get 0.032 kcal per mole. Don't forget the per mole Kelvin part. Calories cancel. Now that we have those 2 things done, we can just plug them into the equation. Where's our equation? Here it is. Delta G equals delta H minus T delta S. You will totally have this on your resources page for exam 3. And you'll need to make sure you have quick access to the table up here. One of these 2 tables. Okay, probably this bottom one. It's more comprehensive. All right, now that we have these, we're just going to plug it into our equation. Calculate delta G. So delta G equals delta H, and our delta H is negative 31.3 kcal per mole. And I like to write them as an actual fraction. Remember, kcal on top, mole on bottom, instead of writing it how it's typed there. And then you're going to do minus. I put it all in brackets. We're going to plug in our temperature, 300.15. Don't forget the 0.15 Kelvin times 0.032 kcal per mole times Kelvin. So do what's in the brackets first, or put it all in your calculator. Just make sure you use parentheses. You should get the right number. It should do the multiplication. I would put it in parentheses just to be safe. Your T delta S part. Anybody tell me what you get for delta G? Negative 40.9. Everybody get that? Negative 40.9? Okay, great. So I'm just going to write it down here. Equals negative 40.9. What are your units? Kcal per mole. There we go. Negative 32.26, maybe. Type it in again, double check. 300.15 times 0.032. And then do negative 31 minus that. They're both negative numbers. I can double check it if I need to.
I got negative 40.9 as well.
Okay. And then 9.60, 9.60. So now do negative 31.3 minus 9.60. Yep, should be negative 40.9 is what I got. Okay, there's even more of these questions, okay? I was going to summarize something down here. I forget what that is. But We have about 10 minutes left. I told you chapter 7 was dense. Anybody feeling the weight of all this? Anybody feel like, holy smokes, this is a lot of numbers. There's a lot of units. There's a lot of math. Okay, I told you. So I think it's good to just take a break for a second and breathe. And this kind of stuff, let me remind you, requires practice. So if you have noticed, any of you who have looked at the chapter 7 homework, it's a teeny bit longer than usual. Usually you have 20-ish questions. I think I put 30 to 35 questions. Why? It's not because I want to give you more work, but it's because I do believe understanding this and preparing you for that exam takes a little more practice. Okay. Also, I had a very interesting conversation with somebody yesterday. They work with a lot of college students, and I would love y'all's thoughts on this. And you can tell me about other classes as well, but I'm really interested in our class. Compared to, if this is your very, very first semester, you really don't have anything to compare to, but compared to a normal face-to-face semester, do you feel like this semester has been more or less work, or about even? I would love to know y'all's thoughts. Anybody, if you want to comment on that or unmute yourself, do you feel like this has been more, way more work, even?
It depends on the class.
It depends on the
This
class.
class, I feel like it's been less.
Okay.
To
You feel like,
me, I feel like it's been less because the
okay.
homework at the book, that was a lot for me. But I like the mastering chemistry better. I feel
Okay.
like that's cool, but it's been more homework, but it's overall it's been less to me.
Okay. Aaliyah has a unique standpoint because she's taken this course where the homework was assigned via textbook. And now we use the Mastering Chemistry platform to do the homework. I feel like I have to teach myself a lot of things because I'm not an auditory learner. Okay, fair enough. Like, and fair enough. Um, and so everybody has said more, way more, a lot more. And that's what I've heard is the general consensus is that it feels like more work. And I actually agree with you guys. And here's why. If I feel like it's been more work on me too, because it's say you do a whole worksheet instead of now just going and handing that to your instructor. Now you have to literally go put all your answers in on Blackboard. That takes more work. Okay. At my other school, my first degree, we used sapling mastering. It's so much easier to use and understand. Okay, that's what I heard about the reviews for mastering, so that's why I chose mastering, and it's more cost effective for you guys. Okay, it's less expensive. What else? So, anyways, I wanted to check in on how that is for you all. I definitely care. The Zooms and stuff is so easy to get distracted, and you have to go back and rewatch, and it's time consuming. Okay, like, and thanks for that comment. That's why I try to do polls. Do y'all feel like doing a poll question helps with retaining your attention on a Zoom? Okay. Sorry, I didn't have any of those today. It's more work in my realm too. It takes more work to go in and type all those in and type the answers in and get them scheduled and blah blah blah. But that's not an excuse. I definitely want to do things that help retain attention for you guys because I think we're all doing our best here. I really do thank you all for doing all this stuff. I know this is not the only class you have. I can say I've not given you more assignments that I would give in a normal semester. The number of labs we do actually might be one or two less. And the number of homework assignments is the same. The number of quizzes is the same. And the number of exams is the same. Yeah, the polls are very similar to clicker questions, Caitlin or Kate. So it's not that I have more assignments on the syllabus. It's just that I agree it's more work in some way. So all this to say, I thank you guys for doing it. I know that it's tough, but if there are ways I can continue to make it easier, ideas that you guys see are happening in other classes, please share those with me. I think the Zoom breakout rooms have been great. I think the group me was a great addition. I wish we'd been doing those things from week one. So in the spring, if we're all online, I hope we're not, but if we are, I'll be doing those things as well. I feel like it's a lot better to be around other people and you can connect with one another than over a screen. I agree. I miss doing class in person. That was the best thing about my job is honestly interacting with you guys in lab. I would get to talk to you guys and have more conversation. I feel like the Zoom breakout rooms have helped a little bit. I've gotten to at least chat with you all a little bit for those that come. Seth said the only thing I worry about is turning everything in to the to the right place at the right time. For the exams, did you ever give study guides? First, Seth's comment. Aaliyah said no, LO. I do review sessions. Is that a helpful kind of study guide? That's fair,
Yeah,
right?
it is, but it was like, we study this, but it's not on the exam. So it was like a win-win situation. It just depended.
So you feel like there are things we did on the review that are not on the exam?
Well, they're on the exam. It's just worded different, and then you're like, oh, I'm gonna work it this way, but it's really another way to work it. It could just be me.
Hmm. Okay.
It probably is just me.
I will say for conversion problems, there's multiple ways to work those. I see people have creative ways all the time. I've tried to always say, just because I work it a certain way in lecture, I'm not going to sit here and think that's the best way to work it. It's just the way that I teach it. I think it's, when you understand units, it seems to be the most streamlined way. But other people have ways that are easier for them. And I'm not going to say if you get to the right answer that you can't work it your way. So I agree with you, Aaliyah. There are multiple ways to work problems sometimes. But I always try to teach you how a way to work it to get the right answer. Yeah, I have not provided study guides. Here's what, but I also sometimes I'm not sure like what students necessarily would want in a study guide. Is that just like a list of concepts of things to study? Because in the past, these first two exams, we did come up with a list. I said list 9 or 12 topics you think are going to be on exam 1 or exam 2. So I have tried to provide a list of topics, like a checklist for you to go back to when you study. I didn't say here's a study guide, but we did come up with a list of concepts. If I did come up with a study guide for an exam, what is a helpful study guide? Is it here, work these problems? Is it here are the concepts, definitions, and work through practice problems, and then a couple to try on our own? The review opportunity is the same as a study guide. Okay. So Lakin wants a full out resume of the exam. Okay. Here are your definitions. You want it all defined up for you. Okay. You know what? Maybe over semesters I could develop those. That would definitely be more work. But I, I feel like if you have your lecture notes in some ways, and again, it's not all pieced together in one pretty perfect document, but if you work the problems with me on your lecture notes, you actually do have work through practice problems. They're just not right there in one nice little neat document. They're spread out through your lecture notes. So I know it's a large study guide, but hopefully your lecture notes are a good study guide in some ways. Anyway.
Also, the review thing that, well, like, I don't know, the review session we did on Zoom, I liked that a lot. It helped out a lot for me.
Okay. Any other comments on that? Anybody feel like it was a waste of time? I can take constructive criticism. Anybody have any constructive criticism you would like to put forth? It's a safe place to do it. Like the review. Okay. I want to be learning. I don't have the corner market on how to do an online chemistry class. I don't own that, and I don't know if anybody does, but I want to get better all the time. So hopefully, we'll pick back up Thursday with lecture stuff. I feel like we've done enough for today. We didn't get as far as I wanted to get, but we'll try to get we'll try to finish the rest of it on Thursday. But hopefully this kind of conversation is helpful for all of us. I think it's good to take a second and self-reflect on how class is going. I reflect all the time on my effort with you guys. If I'm doing a good job of responding to emails, I'll be honest, there are moments where an email slips through the cracks. But I want to be, diligent with emails. I want to be diligent with spending time doing breakouts and things like that. Okay, people are saying they're very helpful, so that's good. And I'm not going to just toss out the idea of a study guide, okay. If I could potentially come up with one of those for you guys, then I'll try to do that for exam 3 and see how that works. But I also want you to know review and study things. I do want to provide those for y'all through the review sessions that we do, and through any individual Zooms you want to set up or things like that. So, all right, well, we're pretty much at time. Thanks, you guys, for being a part today, and we'll see you on Thursday. If anybody has any questions about what we've covered today or in the past, or just any other questions or any constructive feedback about anything, if you have any questions or you just want to chat, I'll stick around for a few minutes, and I'll see you Thursday, and we'll have the quiz Thursday.